Unfortunately, this is take 2 on video 8 in the series about factoring. I was quite a ways in there and I realized I did something kind of stupid and I made a mistake. I had a number backwards, so it was just best to start over. So here we are. So here's the deal. Originally, when I would teach factoring, what I would want would be for us to just go over factoring, and then separately after the fact, we would at some point talk about solving quadratic equations. And there are basically 3 ways to solve quadratic equations, kind of 4, but 2 of them sort of go together. So you can solve quadratic equations by factoring if you have a factorable quadratic equation. You can use the square root property and completing the square, or you can solve using the quadratic formula. None of this matters to you at this point. But I do want to go ahead and show you how to solve quadratic equations by factoring right now while factoring is fresh. It'll also give you a chance to apply what you've learned about factoring. So I'm going to go ahead and show you how to solve quadratic equations by factoring. Now, keep in mind, so far in this video series, we talked about in video 1, how to find a GCF and factor out a GCF. That's still going to be true here. If you see that your quadratic equation has a GCF, you factor it out first. We then looked at factor by grouping, and I do have an example here where factor by grouping is going to be the quickest way to get your quadratic equation factored and move on from there. We then talked about factoring quadratic trinomials. In the first video, we talked about factoring quadratic trinomials where a was equal to 1. And then in the video after that, we looked at factoring quadratic trinomials where a was not 1. We then started talking about these things called special products. So when you learned how to multiply polynomials, you talk about special products. Well, in this series, factoring, we learned how to undo all of that multiplication. So we looked very specifically at perfect square trinomials. We looked at the difference of perfect squares. And then in the most recent video, we looked at the sum and difference of perfect cubes, okay? All of that could potentially come into this video, okay? So in this video, again, we're just gonna look at quadratic equations, okay, and how to solve them by factoring. Now, quadratic equations look very much like a quadratic trinomial. We just set it equal to 0. And because we have that equal sign, what we're doing when we're solving is we're looking for values of the variable that satisfy the equation. And by satisfy the equation, we just mean what value for the variable is going to make this true, okay? So we're not just factoring and then done. We're factoring and then we're still solving, okay? And the reason we can do that is we have an equal sign. Everything prior to this, there was no equal sign. This is the first video in this series where you had an equal sign, and that equal sign forces us to go a little bit further. All right, so let's go ahead and get started. So let's start with some basics. Okay, we have quadratic equations. Okay, so this is any equation of the form ax squared plus bx plus c equals 0. This should be familiar. We talked about something very similar to this when we talked about quadratic trinomials. And when you're dealing with a quadratic trinomial, you end at c. You don't have that extra equals 0. So here, we're going to take it a little bit further. We're going to find values for x that make this equation true. Some things to know is that a, b, and c are real numbers, such that a doesn't equal 0, okay? So a cannot equal 0. Ooh, cannot equal, let me fix that. A cannot equal 0, okay? These are second degree equations. And so anytime you have quadratic, think second degree polynomial, second degree equation, whatever. And so that means you have to have that x squared term. Without that x squared term, it's not quadratic, it's linear. Okay, so if a were to equal 0, this x squared term would disappear. And then you no longer have a quadratic equation, you would only then have a linear equation. Now, these equations have 2 solutions. Okay, and that's something that you're going to learn. The degree of the polynomial indicates how many real solutions you're going to have, right? So if you have a linear equation, you have 1 solution because it's a first degree equation or polynomial. Okay, if you have a second degree equation, you have 2 solutions. If you had a third degree equation, which you will see a couple of special cases in this video where you do have a third degree situation, you would then have 3 solutions, okay? So for us, we are going to have 2 solutions, and I want you to understand what these 2 solutions are. These solutions represent where the graph of the equation crosses the x-axis. So basically, these solutions are x-intercepts, okay? Now, when you're dealing with a quadratic equation, the graph is called a parabola, okay? And I'm just going to give you a very brief overview of this right now because we're not anywhere near ready to talk about graphing quadratic equations. That'll come up much later. But the graph of a quadratic is a parabola. And in case you're not sure of a parabola, it would look like this, or this. And again, we're nowhere near ready to talk about the graphing of quadratic equations yet, but I just want you to have a general understanding so that when you do talk about graphing quadratic equations, you have at least a little background info. All right, so let's say that we had solutions of -3 and 4. So we had some quadratic equation, we solved it, and we found that x was -3 and x was -4. What that would mean for us is if we were to graph this parabola, and this is merely a sketch, okay, I'm not going detailed at all, but I would have an x-intercept at -3 and at 4, and my parabola would do this. All right. And that's it. So you need to just kind of have an understanding that, hey, you're just solving right now and it's going to feel kind of blank and empty. Like, okay, I found these values that satisfy the equation. Just always keep in the back of your mind that those solutions are actually a much bigger deal. Those solutions tell you where you cross the x-axis. Okay. Now, a couple of things. You will sometimes see something like y equals ax squared plus bx plus c. This is still a quadratic equation. You might even see it written in function notation. F of x equals, that's an F. That looks kind of crazy. You could also see f of x equals ax squared plus bx plus c, okay? These are generally used when graphing, okay? So graphing, you're going to have the y equals or the f of x equals. For us now, we will use ax squared plus bx plus c equals 0, because remember, back here, I told you these solutions are really x-intercepts. And remember, to find an x-intercept, you let y equal 0. So we're using this form. We call it standard form. We use this standard form for solving because really what we're doing is we're finding the x-intercepts, okay? Now, that leads me to this next topic. All right, let me see if I can make that straighter. Gracious, that's not much better. But anyway, we're going to use this standard form. Now, this leads me to something called the zero product property. Now, in math, when you deal with properties, properties are just statements or facts that we know to be true. Okay, so for example, x times 0 is always going to be 0. That's a property that's actually going to come into play here. Another property is the commutative property. It means if you add or multiply numbers, you can change the order. No big deal. You could have the division properties of 1. That means a number divided by itself equals 1. A number divided by 1 is just that number. Tons and tons of properties we use all the time. And sometimes we use them so much that we don't even think about them being a property. But this is one that is super duper helpful at this point. This property says, if you have a product AB and it equals 0, then A equals 0 or B equals 0 or both A equals 0 and B equals 0. So in short, if you're dealing with, I've got somebody trying to call me. Hold tight, I'm going to pause. Okay, sorry about that. So anyway, if you have a product AB and it equals 0, then either A or B has to be 0, or both A and B can be 0, but at least one of your factors has to equal 0. So basically, if a product equals 0, then at least one factor equals 0. Okay? So this is generally pretty easy to wrap your head around because we do have something called the multiplication property. And it states very clearly that anything multiplied by 0 is just 0. Okay? So anything multiplied by 0, if I have 7 times 0, that equals 0. And notice, one factor is 0. But we can look at it much more abstract. What if I said 7x equals 0? Well, I don't know what x is, but I know that I've got two factors. I've got a factor of 7 and a factor of x. X has to equal 0. And x has to equal 0 because 7 times something has to equal 0, and the only something x can be is 0. That's the only way to get that 0 product, okay? And this becomes huge for us in this particular concept, okay? So what we're looking for is we're going to look for a quadratic equation that we can break down into the point where it is written as a factor or as a product of factors equal to 0. And if that's the case, we can use this product or this property really easy. So let me show you. So we're going to use the 0 product property to solve. Now, I'm going to give you quadratic equations that are already broken down, okay? But let's say that we have x minus 5 times, times x plus 3. And let's say that equals 0, okay? So x minus 5 times x plus 3, if you were to FOIL that out, you would get a quadratic expression, okay? But we're going to leave it in factored form. Now, we have a product equaling 0. We have two factors. We have x minus 5 and x plus 3. One or both of those factors has to be 0. So what we do is we set each factor on its own equal to 0, and then we solve. All right, so if I say x minus 5 equals 0, I would add 5 to both sides, and I would get x equals 5. If I said x plus 3 equals 0, I would then subtract 3 from both sides, and I would say x equals negative 3. Well, let's check them. So if I let x equal 5, I'm going to plug that back in the original equation. I would get 5 minus 5 times 5 plus 3, and it better equal 0, right? Well, 5 minus 5 is 0. 5 plus 3 is 8, but what is 0 times 8? Well, according to the multiplication property of 0, something that you learn at the beginning of your math career, you would have learned something like this when you were almost a kid. This has to equal 0. All right. Now, if we check, let me move my check symbol over here. Now, let's check the other one. Here, we're going to let x equal negative 3. So if x is negative 3, I get negative 3 minus 5. I get negative 3 plus 3. And again, it dang well better equal 0, right? Well, negative 3 minus 5 is negative 8. Negative 3 plus 3 is 0. So there you have it. Both solutions work. So the way we would represent our final answer is we would put those two solutions in these curly braces, and this represents your final answer. Okay, now let's look at another example. This one's only going to be a teeny tiny bit more complicated because we'll end up with a fraction. So let's say we have x plus 6 times 4x minus 3 equals 0. So again, I have a product equaling 0. My two factors are x plus 6 and 4x minus 3. Now remember from the previous slide, the 0 product property says if a product equals 0, then at least one factor equals 0. So one or both factors could equal 0. So what we do is we take these two factors and we set them equal to 0. Now, if x plus 6 is 0, I would subtract 6 from both sides, and that would tell me that x is negative 6. Let me get some water really quick. Now, if 4x minus 3 is 0, I would start by adding 3. So I would get 4x equals 3. I would then divide by 4, and this would tell me x is 3/4. Well, let's check. Now, if x is -6, I plug this in, I get -6 plus 6, and then I get 4 times -6 minus 3 equaling 0. Well, -6 plus 6 is 0, and it doesn't matter what 4 times -6 minus 3 is, but let's go ahead and simplify it. 4 times -6 is -24, minus 3 is -27, and then 0 times -27 is 0. All right, let's say we check the other solution. This one's going to be a little more complicated because you have that fraction, but it's no big deal. We get 3/4 plus 6, and then I get 4 times 3/4 minus 3 equals 0. Well, 3/4 plus 6 is just 6 3/4. All right. And then if I look at 4 times 3/4, the 4's cancel, and I'm really just left with 3 minus 3. So this is actually just 0. And 6 3/4 times 0 is just 0. So both solutions really do work. We checked them. And our final answer is going to be -6 3/4. And there you have it. So that is how you would solve something that truly is quadratic using the zero product property. Now, it doesn't have to be quadratic. It just so happens in this case, both of these would have been quadratic equations if they were multiplied all the way out. But I wanted you to see how to apply the zero product property all on its own. Okay. Now, from here on out, we're going to look at equations and how to solve them. So steps to solve. Oops, let me go back to black. So the first thing we have to do is we have to make sure our equation is in standard form, okay? So put the equation in standard form. And in case you can't remember, standard form is this right here. Standard form is ax squared plus bx plus c equals 0. So the squared term, then the linear term, then the constant, then equal to 0, okay? So put the equation in standard form, factor the quadratic side, and then step 3, apply the zero product property. And then I like to add this one, write your answer in set notation. So write it as a solution set. Okay, so let's go ahead and start. Let's look at some examples. So we're going to start with some easy examples, and then we'll look at some, more complicated or more involved examples. So first of all, we have x squared minus 4x minus 21 equals 0. So you have to ask yourself, first of all, is this in standard form? Yes, it is. We've got the squared term minus the linear term minus the constant equal to 0. Now, the good news here is the coefficient on the squared term is 1. So we can do that shortcut factoring where we just start two binomials with x, and then we have to fill in the factors. So we're looking for factors of -21 that would add up to be -4. Okay, so factors of -21 could be -21 and 1, or -7 and 3. Now, I only have two sets of factors because if I have a constant of -21, the two factors that I'm looking for have to have different signs. One has to be positive, one has to be negative. And this right here, the coefficient on x tells me the sign of the larger factor. This means the larger factor has to be negative. So the set of factors that works will be -7 and 3. So I'm going to fill in a -7 and a +3. And now I am set up just perfectly to do the zero product property. I'm going to take each factor, set it equal to 0, and then I'm going to solve. So here, x minus 7 is 0. I would add 7 to both sides, and I get x is 7. X minus 3 is 0, so I would subtract 3, and I get x equals -3. Now, before I write out my final answer for this one and only this one, I'm going to go ahead and show you how to check your work, okay? And then after this, it's up to you whether or not you check. So we're going to start by checking x equals 7. So I plug 7 in for x in the original equation. Well, 7 squared is 49. And then 4 times 7, I'm going to get minus 28. And then minus 21 is 0. And then 49 minus 28 is 21. 21 minus 21 is 0. So 7 works. Let's go ahead and check. X is -3. So I get -3 squared minus 4 times -3 minus 21 is 0. Okay. So let's see here. I get -3 squared is 9. -4 times -3 is plus 12. Don't forget your minus 21 equals 0. Well, 9 times 12 is 21. 21 minus 21 is 0. So everything checks out. And I would say my final answer is -3.7. Okay. I'm sorry. Somebody keeps texting me during this video, which is sort of annoying. But anyway. All right. So we can say with confidence that our final answer would be x is 3, x is -3, x is 7. Now, I'm not going to check all of the solutions just for the sake of time in this video, but that's how you would go about doing it. Okay, let's look at some more examples. Let's say this time I have z squared. Go back to black. I keep forgetting to change my color. Let's say I have z squared minus 20. Whoa, that looks a mess. Minus 24 equals 5z. Now, this is definitely a quadratic equation. We have that z squared. The issue is this is not in standard form. So the first thing I want to do is put this in standard form. So I'm going to subtract 5z from both sides. And what that's going to do is that's going to give me z squared minus 5z minus 24 equals 0. Okay, now I have a standard form quadratic, and luckily the coefficient on the squared term is 1. Okay, so I need factors of -24. That means 1 positive, 1 negative, and this -5 right here tells me the larger factor is going to stay negative. So I could try -24 and 1, -12 and 2, -8 and 3, or -6 and 4. So the one set of factors that works is -8 and 3. So because the coefficient on the squared term is 1, I can just jump right to it. I can say I have z minus 8 and z plus 3. Now I take each factor all on its own, and I set it equal to 0. If I have z minus 8 equals 0, I add 8 to both sides, which gives me z equals 8. If I have z plus 3 equals 0, I subtract 3, and then I get z equals -3. So the solution here would be -3, 8. And that's it. Kind of fun, kind of easy. It's not the worst thing you'll ever see. Now, next up, I have y squared plus 12y equals -36. So again, I have a situation that's not in standard form. So what I want to do is I want to move that 36 over. I would add 36 to both sides. So this becomes y squared plus 12y plus 36 equals 0. Okay. Now, again, I'm in a situation where the coefficient on the squared term is 1. So this would be really easy to just go ahead and find factors of 36 that add to 12. You might also notice that this is a perfect square trinomial, so you could factor it using the perfect square trinomial shortcut. Whatever you prefer, let's say you just want to do the traditional factoring. I start each with a y, and then what are two positive factors of 36 that add to 12? Well, 6 and 6. Now notice these are exactly the same. So I subtract 6, I subtract 6, I get y equals -6, I get y equals -6. So what we do is we actually have a repeated solution. You only write the -6 once. And what I want you to know about this is if I was graphing, this graph doesn't cross the x-axis, it just touches the x-axis. So this one would be a little bit different than what I showed you over here. Over here, we had two solutions, okay, and we crossed the x-axis at -3 and 4. But here, we only have the one repeated solution. So what happens there is it's like your parabola just tap dances on the x-axis. It never actually crosses, okay? Now, let's say next up we have 2x squared minus 5 equals -3x. Well, the first thing you're going to want to do is put this in standard form for sure. So I'm going to add 3x to both sides. That would give me 2x squared plus 3x minus 5 is 0. And unfortunately, you do not have a coefficient of 1 on the squared term. This isn't like a huge ordeal. It just does lengthen the process a little bit. So I have found that students really love examples like the first two on the screen because you don't have to do the longer version of factoring. But this isn't too bad. Remember, when the coefficient on the squared term is not 1, we do the AC method. So I figure out what A times C is. It's 2 times -5. So A times C is -10. Now, what I want to do is I want to find factors of -10 that add to 3. So I need factors that have different signs, and I want the larger factor to be positive. So I could do 2 and -1 or 5 and -2. So 5 and -2 works. So hopefully you'll remember that what we do is we rewrite the polynomial. And what we do is we rewrite that bx term and we write it as two terms that would add up to bx. Okay, so I get 2x squared, but instead of 3x, I'm going to write plus 5x minus 2x, and then minus 5 equals 0. So this minus 2, or the plus 5x minus 2x, if I simplify it, what do I get? Well, I just get that 3x that I originally had. And now we factor by grouping. So looking at the first two terms here, I can factor out an x. When I factor out x, I get 2x plus 5. On the right, it looks like I don't have a GCF. So if I look at -2x minus 5, I don't have a GCF, but my lead term is negative, so I still have to factor out a -1. When I do that, I get 2x plus 5. Don't forget, you're still equal to 0. Now, the stuff in parentheses matches, so that's my new GCF. So I've got 2x plus 5. And when I factor that out, I'm left with x minus 1, still equal to 0. So 2x plus 5 equals 0. X minus 1 equals 0. So here, 2x minus 5, I would subtract 5 from both sides. And then I would divide by 2. And then x minus 1, I just add 1 to both sides. So I get x equals 1. So the solutions that satisfy the equation 2x squared minus 5 equals -3x would be -5 halves and 1. And that's it. All right. Let's look at some more examples. I want to make sure we get plenty of practice in. That's basically the same. No, that's different. So let's look at this one. I have 3 plus, oh Lord, I don't know what I just did there. I have 3 plus 5x equals 2x squared. Okay, so we're not in standard form. So what I want to do is I want to subtract 5x and I want to subtract 3 from both sides. So what that will give me is 2x squared minus 5x minus 6 equals 0. Whoa, minus 3. I was getting ahead of myself there. All right, so the coefficient on the squared term is not 1. So we do have to do the AC method. So A times C is 2 times -3 or -6. So now I want factors of -6, and here's the deal. They have to have different signs, and I want the larger factor to be the negative. So I could use -6 and 1 or -3 and 2. So which pair of factors adds up to -5? Well, -6 and 1. So what I'm going to do is I'm going to rewrite this -5x, and instead of writing it as -5x, I'm going to write it as -6x plus 1x. So I get 2x squared minus 6x plus 1x. And then don't forget your minus 3 equals 0. I now factor by grouping. So on the left, I have 2x squared minus 6x. I have a GCF here of 2x. When I factor out a 2x, I'm left with x minus 3. Now, looking at the second half of the equation, I have x minus 3. It doesn't look like I have a GCF, but with or without a GCF, you still have to factor out either a 1 or a negative 1. So in this case, I'm going to factor out a 1. And when I do that, I'm just left with x minus 3. Don't forget you're equal to 0. Sorry, I was getting a sip of water. Now notice the stuff in parentheses matches. So that's your GCF. So I get x minus 3. And then the other GCFs, those little GCFs that you had, they always go down here. And don't forget we're equal to 0. So x minus 3 is 0. 2x plus 1 is 0. If I have x minus 3 is 0, I just add 3 to both sides, and I get x equals 3. For 2x plus 1 is 0, I subtract 1. That gives me 2x equals negative 1. And then I divide by 2. So the solutions here would be negative 1/2 and 3. It's kind of fun. I think this is fun anyway. Anything involving factoring, I enjoy. All right, let's try this one. So let's say for the next example, I have 5x squared plus 3x minus 1 equals 3 minus 5x. Now, on the surface, this might look like a mess, but it's really not. We want to put this in standard form. And one thing I will advise you of is when you put your equation in standard form, always put your equation in a standard form so that the squared term stays positive, okay? So that means we're going to move the 3x we're going to move the 3 and the 5x. So let's see, we get 5x squared plus 8x minus 4 equals 0. Okay. So now you've got a coefficient on the squared term of 5. So we have to do the AC method. So A times C, now that we're in standard form, is going to be 5 times negative 4 or negative 20. Now we need factors of negative 20 that add to positive 8. Those factors, one has to be positive, one has to be negative. And this right here tells me that the larger factor is positive. So I could use 20 and negative 1, 10 and negative 2, or 5 and negative 4. So which pair of factors adds up correctly? Well, 10 and negative 2. So I'm going to rewrite this polynomial. So I get 5x squared, and then instead of 8x, I'm going to write it as plus 10x minus 2x. And then I'm going to write down the minus 4 is 0. So I factor by grouping. Looking at the left, I have 5x squared plus 10x. My GCF is 5x. When I divide both of those terms by 5x, I'm left with x plus 2. Let me fix my plus sign. It looks kind of crazy. And then looking at the right-hand side of this equation, I have negative 2x minus 4. My GCF here is negative 2. So when I factor out negative 2 from negative 2x and negative 4, I get x plus 2. Don't forget we're equal to 0. The stuff in parentheses matches, so that's my new GCF. So I get x plus 2. And then those original GCFs, those little GCFs, they come down, and I get 5x minus 2, still equal to 0. So I've got a product equaling 0 now. So I take x plus 2, set it equal to 0. I take 5x minus 2, set it equal to 0, and then I solve. So for x plus 2 equals 0, I subtract 2, and I get x equals negative 2. For 5x minus 2 equals 0, I start by adding 2 to both sides. That gives me 5x equals 2. And then I divide by 5, and I get x equals 2/5. So my solutions are negative 2 and 2/5. All right. So it's not the hardest thing ever. You do need to be neat and organized. And if at any point you feel like your answer doesn't make sense, check it. Remember, the way you can check, we did that on a previous example. Let's see, we did it right here. So we went ahead and we solved this equation. This is our first quadratic equation that we solved start to finish. We factored, we got x minus 7, x plus 3. We found our solutions to be 7 and -3. And the way you check them is you plug the value for x back into the original equation and work it out. All right. So if at any point your answers, you're like, I don't know, go ahead and check your work. I'm not going to do it for every problem here just for the sake of time, but you can always check your answers. All right. So let's do a few more. I've got, let's see, maybe 3 more. So let's say that I have, well, 4 more. Let's go back to black ink first of all. So let's say I have x times x plus 1 equals 2. Now, you got to be careful. You cannot get ahead of yourself, all right? Over here, we had something that was already factored, but it was equal to 0. Notice we had equal to 0 in both cases. So we could jump straight to the zero product property, but that's not what we're working with here. The issue here is we're not equal to 0. We're equal to 2. So what we have to do is we have to do a little work to get this into standard form. So I'm going to start by distributing x. So x times x is x squared, and then x times 1 is x. That still equals 2. Now to finally get this in standard form, I'm going to subtract 2 from both sides, which gives me x squared plus x minus 2 equals 0. Now the coefficient on the squared term is 1. Okay, so I can go ahead and do the short version of the factoring where I just jump to 2 binomials, starting each with an x. And now I need factors of -2 that have different signs, and they would have a sum of 1. So I could use 2 and -1 or -2 and 1. So which set of factors works? Well, 2 and -1. So I would come down here, I'll go x plus 2. X minus 1 equals 0. So now I'm going to take each of these factors, I'm going to set it equal to 0. Now, if I have x plus 2 is 0, I subtract x, or I subtract 2 from both sides, and I get x is -2. If I have x minus 1 is 0, I add 1 to both sides, and I get x equals 1. So my solutions would be -2 and 1. Sorry, my throat is so dry, so I keep drinking water. All right, let's try another one. So next up, let's say I have x plus 5 times x minus 3 equals 9. So this is the same situation. It looks very similar to what we did here, where we had 2 binomials multiplied together, but they were equal to 0. So if we had a product that was automatically equal to 0, we could go ahead and apply the zero product property. That is not what's happening here. We're equal to 9. So the first thing we want to do is FOIL, and then we'll move the 9 over and simplify, and then we'll be in standard form. So x times x is x squared. X times -3 is -3x. 5 times x is 5x. And then 5 times -3 is -15. And I'm going to go ahead and subtract my 9 over. All right. So when I clean this up, I get x squared plus 2x minus 24 equals 0. Now, the good news is the coefficient on the squared term is just a 1. So we can jump to the easy factoring. I need factors of -24, and I want the larger factor to be positive. That way, when we add, we'll get that +2. So I could have 24 and -1. I could have 12 and -2, 8 and -3, or 6 and -4. So which pair of factors works here? Well, 6 and -4. So I start 2 binomials with an x, and then I fill in those factors. I go +6 minus 4, and honestly, the order that you fill in the factor doesn't matter. I could have easily done -4 first, +6 second. The only thing that matters is the sign in front of the factor has to be correct. Okay, so I can apply the zero product property. I have x plus 6 is 0. I have x minus 4 is 0. Now I'm going to subtract 6. So x equals -6. For the next factor, or the next little equation, I'm going to add 4. So I get x equals 4. And there you have it. So these two examples, it's not that they're very difficult. You just have to be really careful because you're not equal to 0. You're equal to some other value. So you have to do some work. You have to distribute. You have to FOIL. You have to move things around. You're not in standard form. You're not ready to use the zero product property first. Okay, so you got to do some work first. Now, for the last two examples, we actually have something that's a degree 3 equation. And if we have a degree 3 equation, you should expect 3 solutions. So let me show you. So first up, we have 2x to the third plus 2x squared minus 12x equals 0. And so what I noticed about this equation right off the bat is I have a trinomial, no big deal, but I have too many x's and I have a big old factor of 2. So what I want to do is I want to factor out a 2x. So here I have a GCF equal to 2x. So I'm going to factor that 2x out. And when I divide all of the terms by 2x, I'm left with x squared plus x minus 6. All right. So I have to keep track of that 2x. It matters because it has an x. It's still part of the zero product property when we go to the next step. But for now, I'm just going to focus on what's inside the parentheses. Clean that up a little bit. All right. So inside the parentheses, I'm just going to rewrite my 2x for now. Inside the stuff in parentheses, you do have a coefficient of 1 on the squared term. So I know I'm going to have two binomials that are both going to start with an x. But what I'm going to do now is I'm going to find factors of 6 that add to positive 1. So I could use 6 and negative 1, or I could use 3 and negative 2. So which pair of factors of negative 6 works for us? Well, 3 and negative 2. So I'm going to fill in a minus 2 and a plus 3. And then now I have 3 factors in this product equaling 0. So I'm going to have 3 equations to solve. Well, 2x equals 0, you can either just apply the zero product property or you can divide both sides by 2. Either way, x equals 0, that's one of our solutions. And then if I have x minus 2 equals 0, I would add 2 to both sides. That gives me x is 2. And then finally, x plus 3 equals 0, I would subtract 3 from both sides, and I get x is negative 3. So my solutions would be negative 3, 0, and 2. All right. Let's do one more. Am I happy with one more? Yeah, I'm happy with one more. Let's do one more, and then we'll call it a day. Maybe I do want to do 2. We'll see. Maybe 2 more. All right. Next up, I have x to the third plus 3x squared minus 4x minus 12 equals 0. So in this particular case, we have factors of x's, we have factors of 3, factors of 4, but we don't have a common GCF. But we're old pros at this. This right here is a polynomial with 4 terms, and your gut should tell you, you know what, I should factor by grouping. So if I look at just the left 2 terms, x to the third plus 3x squared, I need to factor out a GCF of x squared. When I do that, I get x plus 3. If I look at the second 2 terms, I have negative 4x minus 12. Here, my lead term is negative, so my GCF has to be negative. So I'm going to factor out a negative 4. When I factor out negative 4, I'm left with x plus 3. So my GCF is x plus 3. And then I have x squared minus 4 equals 0. Well, hopefully somebody watching this is like, oh, wait a minute, x squared minus 4, that looks familiar. Should look familiar. What is x squared minus 4? Well, x squared minus 4 is the difference of squares. So my x plus 3 is still good. But x squared minus 4 can be factored. I need to find the square root of x squared, which is x. I need to find the square root of 4, which is 2. And then to factor the difference of squares, we add the square roots and then we subtract the square roots. So notice you have a degree 3 polynomial or a degree 3 equation. You are going to get 3 solutions. Your first solution is going to be found from x plus 3 equals 0. Your second solution will be found from x plus 2 is 0. And your third solution will be found from x minus 2 is 0. So x plus 3 is 0, I subtract 3. X equals negative 3 is one of my solutions. X plus 2 equals 0. I subtract 2. And x equals -2 is one of my solutions. For x minus 2 equals 0, I add 2, and x equals 2 is my third solution. So my solutions would be -3, -2, and 2. All right. Now, last up, we're not going to get a degree 3. We do have a second degree polynomial, but let's look at this one. I have 3x squared plus 7x equals 7 times x plus, Lord have mercy, is that 21? I might not have that right, but let's go ahead and go with it. All right. So I'm going to go ahead and distribute the 7 over here on the right. So I end up with 3x squared plus 7x equals 7x plus, let's see, 147. Now I want to put this in standard form, and remember, you always want to put your equation in standard form in such a way that the squared term remains positive. Okay, so I'm going to subtract 7x and I'm going to subtract 147 from both sides. All right, everything on the left cancels, so I end up with 3x. And then notice here on the left, or everything on the right cancels. On the left, I have a 7x minus a 7x. Those cancel. So I really end up with just 3x squared minus 147 equals 0. Well, let's see, is 147 divisible by 3? Yeah, so we have a GCF of 3, okay? So when I factor out that 3, I get 3 times x squared minus 49 equals 0. Now, I'm kind of glad this one comes up because on the previous slide, when we factored out our GCF contained an x. Okay, so that x was valuable. It contained a solution. You could also see that we had a degree 3 polynomial. Well, on this slide, we have a degree 2 polynomial, and this does not contain an x. So look at what I'm going to do here. I'm going to take both sides of this equation and I'm going to divide them by 3. 3 cancels and I'm left with x squared minus 49 equals, well, 0. You got to be careful here. This GCF of 3 is like the fat you trim off the steak and you give the dog. It doesn't do anything for you. And it's very different than this 2x GCF. The 2x was important because it had an x. That x indicates a crossing of the x-axis, whereas this 3 just indicates fluff, okay? So if you have a GCF in a situation like this that is just a number, divide both sides of the equation by that value, and then you don't have to worry about it. So now we have x squared minus 49, which is the difference of squares. Now for the difference of squares, you take the square root of x squared, which is x. You take the square root of 49, which is 7. You add, and then you subtract. So now I get x plus 7 equals 0. I'm almost out of space, so we would subtract 7 from both sides. So that gives me x is -7. I then have x minus 7 is 0. So I would add 7 to both sides, and I would get x equals 7. And then finally, my solution would be -7, 7. So there we have it. All right. So just be careful of this very last example compared to this example right here where we had the GCF of 2x. They're wildly different. And what I really want you to notice is that GCF of 2x is part of the solution because we did have a degree 3 polynomial. Whereas in this case, we didn't have a degree 3 polynomial or a degree 3 equation. We had a second degree equation, which means we only get the 2 solutions. Whew. Okay. So this is like, I think, my 4th video today. So my voice is pretty well shot. I'm kind of tired, I guess. I don't know. I just need to rest my voice. Anyway, so this wraps up the factoring series of videos, okay? The first 7 videos in the series were just on factoring. This 8th video, ordinarily I would save solving quadratic equations for when I do, solving quadratic equations later, because there are other methods for solving, because what's going to happen is some quadratic equations can't be factored. And so when you have a quadratic equation that can't be factored, you do have other methods. You have completing the square, or you have this thing called the quadratic formula. But since we had just done factoring, I felt like, why not go ahead and teach it now? You can apply what you've already learned with factoring, and you can practice this method while factoring is still fresh on your mind, okay? So this does wrap up this video series. The next video series that I would work on would be rational expressions and rational equations. And what I would caution you about that material is you have to know how to factor. If you're not really strong at factoring, you're going to have zero success at adding, subtracting, multiplying, dividing. Rational expressions, you're going to have a hard time simplifying rational expressions, and you're definitely going to have a hard time solving rational equations. Factoring is huge. It's as big in rational expressions and rational equations as it is now. Okay, so if you're already in rational expressions and rational equations and you're struggling, go back, figure out your factoring first. Okay, you've got to be really, really strong at this stuff before you move into rational stuff. All right, so I will start that next video series. Definitely not today. My voice is shot. Maybe tomorrow. All right, take care.